The Morning Show.
We are continuing our conversation of the digital thermometer. Today, we try to understand why one of those requires you to have a clean forehead and what that has to do with how much thermal radiation a tomato gives off. Here's wise guy Paul Kwiat.
Hey everyone, nice to see you. Hope you're getting all ready for the New Year's, whatever celebration you can have in these times. So we've been talking about this thermometer, digital thermometer, and the way that it works is the fact that anything that's warm, like me, will emit thermal radiation, electromagnetic radiation. And this has this little infrared sensor up at the top, and it records how much power is being emitted and converts that into a temperature. So they say anything that's warm will emit thermal radiation, and the warmer it is, the shorter the wavelength. So something like the sun or like a light bulb is going to emit in the visible that we can see. Something that's like a body temperature is going to emit around 10 microns, so wavelength. So we can't see that by eye, but this can detect that. Now, the reason it works, we said, was that how much power is emitted depends quite sensitively on the temperature. So it's the fourth power of the temperature. So that means the temperature doesn't have to change very much for the power to change quite a bit. So then that's easy to detect. It turns out there's another property that determines how much power is emitted, property of the object that's emitting, and that's called the emissivity. And that ranges anywhere from 0 to 1. And I just want to understand that a little bit more because it leads to another interesting fact in the instructions about how to use the thermometer. So the emissivity, well, first, let's just go back. We've talked in previous Wise Guys last week and other weeks about the second law of thermodynamics, which says that I want to maximize the total entropy of a closed system. The entropy is the total number of ways of sort of configuring that system. And in equilibrium, that'll be a maximum. So if I have an object that's in a surrounding room, and initially they're not at the same temperature, they will exchange energy. And as they exchange energy, the total entropy is going to increase until they're at the same temperature, and then the total entropy will be a maximum. So another way of understanding the second law of thermodynamics is that when two bodies are at the same temperature, there won't be any spontaneous heat flow between them. That would violate the second law of thermodynamics. Okay, so what does this have to do with our emissivity that we've been talking about? So let's say that I have an object, say this red ball that's at some temperature T, and it's in a room that's at the same temperature, the exact same temperature, but the room is completely empty. It has a vacuum. There's no wires connecting the ball to the room. So the only way that they can exchange energy is by this thermal radiation. And I now want to prove that therefore the emissivity has to be equal to the absorption. So because the object is hot, it's going to be emitting radiation. And because the room is hot, it's going to be emitting radiation, and some of that will be absorbed by the object. And now I want to prove that the amount that's absorbed has to equal the amount that's emitted. And we'll do that in a way that scientists often do using a counterexample. So let's say that that wasn't the case. Let's say that the emissivity was greater than the absorption, so that the object was emitting more power than it was absorbing. Well, if that were true, then the object would spontaneously cool off because it's losing energy. Or if instead the object emissivity was less than the absorption, so if we were emitting less power than we're absorbing, well then, because it's constantly taking in a net energy, it'll spontaneously heat up. And we know that both spontaneous cooling and spontaneous heating are not possible according to the second law of thermodynamics. So the absorption and the emissivity of the object have to be the same. Okay, so one more thing just to try and get a sense of what the absorption is. So let's say I take this tomato or any object and I shine light on it. There's only three things that can happen. Either the light can go through, it can be transmitted, or the light can be reflected in some way, scattered off the object, or the light can be absorbed. And those are the only three things that can happen. And if I have an opaque object like this tomato, then there's no transmission. So either the light is absorbed or it's reflected. So that means that if I have an object that's very reflective, that means it can't be absorbing much. Or if it's not very reflective, that means it would absorb a lot. And because the absorption is the same as the emissivity, that means if I have an object that's quite reflective, that means it's not going to be absorbing as much. That means it won't be able to emit as much thermal radiation. Okay, so now let's say, what does that have to do with my thermometer? So on the instructions, it says to make sure you don't have anything on your forehead, like dirt or for example, perspiration. So why would that make a difference? So I've prepared a little demonstration here. I took some Caro corn syrup, which is very shiny, and I put it on my arm a couple minutes ago, just using a Q-tip here. And so there's this kind of shiny patch on my arm. It's a little hard to see, but anyway, it's right there. You can see it glinting in the light. And now I'm just going to measure what is the temperature on the part of my arm that doesn't have the reflective Karo corn syrup and the part that does. And what do we expect? Well, they all should be at the same temperature because, the corn syrup has been on my arm for quite a while, so it should be at the same temperature. However, because the corn syrup is more reflective, that means it's less absorptive. That means it's also less emissive. So that means I should be getting less power coming out of the region of my arm that has the corn syrup than the region of my arm that doesn't have the corn syrup. And this doesn't know that. It just measures the total amount of power and then converts that into a temperature. So this should think that the reflective part is going to be at a lower temperature than the other part. So let's just do the quick experiment. So this is the part of my arm that doesn't have the Karo corn syrup on, and it says that it is 96.9. And now I'll measure the other part. And this says that it's 96.8. And it's not clear that the resolution of the thermometer is that good. So let's just repeat that measurement again. So again, off to the side, I get 96.9. And on the part that has the corn syrup, I still get 96.8. And when I just put the corn syrup on, it's actually even a little bit smoother, so it reflects a little bit more, and the temperature difference was even a little bit bigger. Okay, so that's why you shouldn't have anything on your forehead when you're using one of these thermometers. Okay, next time we have just one more topic we want to address with this, because there's a really big paradox, which is how can this thermometer work well on someone who's really pale like me, white-skinned, and also on someone who has very dark skin? Because according to the argument I just gave, it should give very different temperature readings for those two people, even though they're actually at the same temperature. So how can that work? Okay, if you think you know the answer to that, please shoot me an email at kwiat@illinois.edu, and we will discuss this next week. In the meantime, have a great week. Bye-bye. Happy New Year.